Thanks so much for being here for the last talk of today, V8 internals for JavaScript developers. But before we get started with that, there is something I have to say. Because when I was a younger boy, I was really into this one video game. I spent countless hours playing it, and it didn't seem to be very popular in Belgium, where I grew up. But on the other hand, it was extremely popular in Brazil. The game is called Tibia. So anyway, through this game, I had my first interaction with people from Brazil. I made lots of Brazilian friends, and I was taught my first Portuguese swear words and stuff like that. And it's actually pretty incredible to me that now, like 10, 15 years later, I'm doing the exact same thing, but in the real world rather than the virtual world, by being here at this amazing conference with all of you. So thank you so much for having me. It's a real honor. And those of you who play Tibia, come find me later. We can be nostalgic together. Anyway, so my name is Mathias, and I work on the V8 team at Google. And V8 is the JavaScript engine that is used in Chrome and Node.js, for example. And today I'm going to give you some performance advice for your JavaScript code. But before we get to the actual advice, we're going to look at some JavaScript engine internals together. So I'm going to be talking about some optimization mechanisms that we use in V8 specifically. However, the performance advice that we'll extract from this knowledge does not just apply to V8 and Chrome and Node.js. It applies to all JavaScript engines and all browsers equally. And really, the most generic, but also the most important advice that anyone can give you today is just to write modern and idiomatic JavaScript code. And just mostly let the JavaScript engine worry about making it fast for you. It's kind of our job to do that. Modern JavaScript features are often more than just syntax. They actually offer more optimization potential than their handwritten alternatives. So don't be afraid to use them, basically. It's a more scalable approach. With that in mind, let's zoom into this thing called elements kinds and what they are and how they work in V8. So JavaScript objects can have arbitrary property names associated with them. You can use literally any Unicode character in them. It could be anything. But one of the more interesting cases that a JavaScript engine can choose to optimize for are properties whose names are purely numeric, and more specifically, array indices. Properties that are numbers that are also valid array indices. So in V8, these array indices are handled specially. Although in many circumstances they behave exactly the same like other properties, V8 actually chooses to store them separately from other numeric properties for optimization purposes. Internally, V8 even gives these properties a special name. They're called elements. So you can think about it this way. Objects have properties that map to values, and arrays have indices that map to elements. These are just the names that we use. So while running JavaScript code, V8 keeps track of what kind of element each array contains. And this information allows V8 to optimize any operations on the array specifically for this type of element. For example, when you call reduce or map or for each on an array, then V8 can optimize the call based on what kind of elements the array contains. So take this array, for example. What kind of elements does it contain? Well, if you would ask the type of operator, it would tell you that the array contains numbers. Because at the language level in JavaScript, that's all you'll get. JavaScript does not distinguish between things like integers, floats, doubles. They're all just numbers. However, at the engine level, behind the scenes, we can be a bit more precise, and we can make this more precise distinction. So the elements kind for this array would be packed SMI elements. Don't worry about the packed part for now, but let's focus on the SMI part and explain what that is. In V8, the term SMI refers to the particular format that we use to store integers. It stands for small integers. So if we have this array and then later we add a floating point number to that same array, the array would transition to a more generic elements kind. In this case, it would be packed double elements. Now, adding a string literal to the same array would change the elements kinds once again. Now it would be packed elements. So we've seen so far that V8 assigns an elements kind to each array, And the elements kind is not set in stone. It can change at runtime based on the code that we as JavaScript developers write. So in this case, we transitioned all the way from packed SMI elements to packed elements. So with that in mind, so far we've seen these three distinct elements kinds. There's SMIs, there's doubles, and then there's regular elements. But you can think of it as a pyramid. The set of numbers that can be represented as a SMI is a subset of the numbers that can be represented as a double, and so on. So you go from very specific element types at the top to more general variants at the bottom. But what's important here is that these elements kind transitions can only go in one direction. You can go from the specific types at the top, like packed SMI elements, to a more general kind, like packed elements. But once you reach the bottom of the pyramid, you can never go back up. You can only go downwards through the pyramid. So if we go back to that array we had before, we started with 3 elements, then we pushed another one, then we pushed another one. So the array contains 5 items at this point, right? Now, what happens if we assign a value to an index outside of the array's bounds? For example, if we assign a value to position 9 in this array, what happens? Well, it turns out that this creates holes in the array at positions 5 until 8. There is no value there. So the array is now sparse, or holy, as we like to call it on the V8 team. Now, creating holes in an array downgrades the elements kind to its holy variant. In this case, we went from packed elements to holy elements. Of course, there are other ways to create holes in JavaScript. For example, if you use delete on an indexed element in an array, that also results in a hole. And there's many more ways of doing this. But why does V8 care whether there are holes in an array? Why does it care so much that it has a separate elements kind just for holes? Well, let's find out together by taking a look at an example. I want you all to pretend you're a JavaScript engine for the next couple of minutes, okay? So we're gonna do an exercise. We want to get the element at index 8 out of this array that we discussed. What is the value for the element at index 8? Now, remember, we're all JavaScript engines, so we have to implement the specification. We can't just blurt out the answer right away, right? We need to follow some steps. So let's do exactly that. We need to do some work. So V8 starts off by doing a bounds check on this array index number 8. Is this index between 0 and the number of items in the array? And in this case, the bounds check succeeds, but we still cannot answer the question of what the result is. We need to do a little bit more work. Now, the next thing that V8 does is it looks up the property 8 on the array itself. But in this case, that property doesn't exist, right? Because there's only a hole. There is no value there. So we still cannot answer the question. We have to dig deeper. Now, because the property is not present on the array itself, V8 has to go up the prototype chain until either a value is found or the prototype chain ends. And first, it checks array.prototype, because that's the prototype of any array. And we find that it doesn't have this property named 8 on it. So at this point, we still do not know what the answer is. We have to continue to follow the prototype chain. And the prototype of array prototype is object prototype. So we check if the property 8 exists there, and it doesn't. So in this case, the prototype chain ends after reaching object.prototype, but it could be longer in case someone extended it, which is something you can do in JavaScript. So because the chain ends here, we cannot continue searching for the property anywhere, which means we can now finally answer our question. The hole at position 8 in this array is undefined. So for the JavaScript engine's perspective, that's a lot of work just to get an undefined value, right? Well, if you compare that to a packed array, which is an array that is guaranteed to have no holes in it, it turns out that if the array index is within bounds, we no longer have to do all those other checks. The engine can already return the value. We don't have to do that expensive prototype chain lookup. And even if we get a property that does exist, but on a holy array, then the engine still needs to check if the property exists first, and then we need to check if the index is within the boundaries, and in this case it is, but then we still don't have enough information to return the result. We must also check if the property then exists on the array itself, because we know there are holes in this array, there could be holes, and maybe there's a hole at this position. So we need to do this extra check. And in this case, the property exists, so then we can finally return the value. If the property didn't exist, then we would be back in the situation from before, and we would have to do that expensive prototype chain lookup with all those additional steps. So what you see here is the absolute best case scenario for a wholly array. And it's still one more operation compared to a packed array. And that is why, in general, these packed arrays are preferred over wholly arrays. Operations on packed arrays can be optimized much more aggressively than operations on wholly arrays. So for optimal performance, it makes sense to avoid creating holes whenever you can. Now, if we go back to that list of elements kinds we talked about, we already knew that there were smice and doubles and then regular elements. And we also knew that you can transition downwards. You can go from smice to doubles and then to regular elements, but you cannot go back up. But now we've learned that there's actually two flavors for each of those elements kinds. There's the packed version and there's a wholly version. And we can also transition from a packed kind to the wholly counterpart. So instead of two different pyramids, it's actually easier to think of these elements kinds as a lattice. And that is also how V8 implements this system around elements kinds and the transitions between them. A little bit more concretely, it looks something like this. So we have our smi and double and regular elements just like before, and each of those comes in two flavors. There's the packed version and there's the wholly version. In total, V8 currently distinguishes about 20 different elements kinds, but these are just the most common ones. And each of those comes with its own set of possible optimizations for every possible array operation you can think of. Now, throughout this lattice, you can only transition downwards. You can only follow the arrows. In this sense, it's kind of similar to that Pokemon Blue tower puzzle where like you step on the tiles with the arrows on them and then you can only move in the direction of the arrows. This is exactly like that. So because of this, because you can only follow those arrows, it has some consequences. Once a single floating point number is added to an array, it will be marked as double forever. You cannot go back up, even if it later consists of smice only. And another example is, once you create a hole in an array, it will be marked as wholly forever, even if you fill it later. So in general, more specific elements kinds enable more fine-grained optimizations. The further down the elements kinds lattice you are, the slower manipulations of that object might be. So for optimal performance, you should avoid needlessly transitioning to less specific types for your arrays. Try to stick to the most specific one that's applicable to your situation. Now, for each unique elements kind, V8 can apply these specific optimizations when performing operations on the array. So whenever you're using array for each, for example, V8 can optimize that call based on whatever elements kind this array has. We can have one set of for each optimizations for packed smi elements, and then another set of optimizations for packed double elements, and so on. They're all different sets of optimizations. Now, this example is from Chrome 59. As you can see, we had implemented this elements kind infrastructure, but Chrome 59 happened to be when we launched an entirely new pipeline in V8. So at that time, we didn't actually use the information to optimize array for each specifically. But by the time Chrome 61 came out, we had already optimized for each in Turbofan, or new optimizing compiler, for all packed elements kinds. And then later, by the time Chrome 64 was released, we came full circle and actually had optimizations for even the wholly elements kinds as well. And this is a pattern that will repeat itself throughout all JavaScript engines. Over time, more and more optimizations will be added, all based on the same infrastructure. So we can say the same thing about array prototype map, or filter, or sum, or every, or reduce right. And then there's these two, array.prototype.find and findIndex. And they are a little bit special. The reason for this is that if you look them up in the spec, you will find that they treat holes in arrays differently from all the other array methods. They turn holes into explicit undefined values, which is something none of the other methods do. And for this reason, it's a little bit hard for us to optimize them in the case of wholly double elements. But we're working on it. And in fact, just this week, a colleague of mine, I was kind of nudging him. I said, look, I'm going to do this presentation for BrazilJS, and it's kind of a shame that I have to present this slide here. The red looks a little ugly, right? And then he was like, okay, just give me a few minutes, and he whipped up a fix, and yep, now it's fixed. So it might become part of Chrome 70. Yep, just for you. So anyway, the point is that even if we don't use this elements kinds information for every possible array operation just yet, over time you will see us add more and more of these optimizations. And as a developer, that's not really something you have to worry about. Things will get faster over time. But let's look at another JavaScript example. This piece of code creates an array of length 3. But what does it contain? Well, it turns out the array just has 3 holes in it. It doesn't have any explicit values. So the array is sparse, and it gets the elements kind wholly SMI elements, because that is the most specific possibility given the current information. Now let's assign a value to position 0 in this array. Wait a minute, that's a string, it's not a small integer. So the elements kind transitions to wholly elements. Now let's assign another value to position 1 in the array. The elements kind remains the same in this case. And finally, we assign a value to the last position in the array as well. So at this point, all the 3 positions in the array are filled. So the array is now packed and it's no longer sparse. However, as we saw earlier, we cannot transition to a more specific elements kind such as packed elements. So unfortunately, the kind remains wholly elements. Once an array is marked as wholly, it remains wholly forever. And I believe that's how sainthood works as well. Now, in this scenario, a better solution is to use an array literal instead. Of course, if you know all the values that you want to be part of your array ahead of time, why wouldn't you just hard code them like this, right? But the more interesting case is when you don't know all the values ahead of time. Maybe you have to dynamically compute some of them or get some values from an API or something like that and then add them to the array later. How would you deal with that situation? Well, what you can do is you can create your array, even if it's just an empty array, and then later you can push the values to it as you dynamically compute them. Because that way, holes are avoided at any point in time, so the array is never marked as wholly. This approach ensures that the array remains packed and that V8 can optimize any future operations on the array properly. Life is easier without holes. JavaScript engines can deal with packed arrays much more efficiently. And in general, if you need to perform lots of operations on an array, then avoid creating holes in it. Similarly, avoid reading beyond the length of an array. Trust me, there's nothing there. So for example, don't write your loops like this. This loop reads all the elements in the array and then one more, because it only ends when it finds an undefined or a null element. I didn't actually make up this code example. There's a very popular library that is using exactly this pattern. They have somewhat of a reason for it, which is old versions of Internet Explorer. Don't ask. But in general, try to avoid this kind of code, because this is just as bad as hitting a hole in an array. In this case, the bounce check that we talked about before, it would fail. And then the check to see if the property is present on the array would also fail. And then we need to look up the prototype chain, which is pretty expensive. So don't do this. And instead, try to keep your loops simple and just keep iterating until you hit the last element. Here's how you could do that with a simple roll your own for loop. Now, when the collection that you're looping over is iterable, which is the case for arrays, but also other things like node lists in the DOM, you can use for of, which I think is even better. This is my favorite way, personally, of iterating through collections. It's just really simple because you don't have to keep track of the index yourself. You just say, I want to loop over this thing and let the JavaScript engine take care of the rest. But of course, if you're dealing with an array specifically, and this talk is about arrays after all, then you could also use for each. So there's these 3 different options, right? You have for each, you have for of, or you have the classic for loop. And the good news nowadays is that performance is no longer a factor in making the decision of which of these 3 you want to use. Which means you as a developer, you can just use whatever you think makes your code the most readable. I personally like for of, but if you want to go with for each instead, that's totally fine. And the performance will be the same. I think that's pretty cool. So avoid reading beyond the length of the array, because it's not exactly the same as hitting a hole, but it's very similar. Now, before we move on to some more performance advice, here's a fun fact. Did you know that JavaScript has 2 different zeros? There's the regular 0, which is positive 0, but there's also a negative 0. So although these values are strictly equal to each other, as you can see here, it turns out that they actually behave differently in some cases. And you can verify this by using object.is, for example. And because they behave differently, of course, JavaScript engines have to store them in different ways behind the scenes. And the reason I'm telling you this is because it has an impact on elements kinds as well. I hinted earlier that it makes sense to avoid transitioning to a less specific elements kind whenever you can. But this is a lot harder than it seems. So for example, let's say you have this array with the values 3, 2, 1, and just a regular positive 0. But just adding -0 to this array of small integers is enough to transition it to packed double elements. And now any future operations on this array will be optimized in a completely different way than they would be for SMIs. It would still be optimized, but just differently. And this is just one more reason to avoid the use of -0 in your code if you don't really need to make that distinction, which I think in most cases you don't. But another example is the values nan and infinity. They have kind of the same problem. They are represented as doubles, which means that adding a single nan or infinity to an array of SMI elements is enough to transition the whole thing to double elements. So if you're planning on performing a lot of operations on an array of integers, then you should consider normalizing -0 to +0 and actually blocking nan and infinity and never adding them to the array in the first place when you're initializing the values. So this way, the array would stick to the packed SMI elements kind, and this one-time normalization cost of doing those checks can possibly be worth the later optimizations that you get. But in fact, if you're doing lots of mathematical operations on an array of numbers, you should really look into using typed arrays, because V8 has specialized elements kinds for those, and it kind of takes care of a lot of this normalization automatically. In general, if you need to perform lots of operations on an array, try sticking to an elements kind that is as specific as possible for your use case, so that V8 can optimize it as much as possible. Now, some objects in JavaScript, especially some objects in the DOM, they look like arrays, but they aren't proper arrays. It's possible to create these array-like objects yourself, which is what I'm doing here. This object has a length, and it supports indexed element access, just like a real array, but it lacks array methods on its prototype, like things like for each, map, and reduce. It is still possible to call these array methods on the array-like object, though. So you can do something like array.prototype.foreach.call, and then you pass in the array-like object, and then you pass in your callback for each, and that actually works as expected. However, this is going to be slower than calling for each on a real array, which is highly optimized in V8. So if you plan on using array built-ins like for each, map, and all those things on this object more than once, then you should consider turning it into an actual array beforehand, so that V8 can optimize the operations based on the elements kind. And here we're doing exactly that by using slice. So of course there is a one-time conversion cost in actually calling slice. You know, it doesn't come for free. You have to pay a certain performance penalty to execute that one line of code. But this cost can be worth the later optimizations that you get when you're actually running your loop itself, especially if you plan on performing lots of operations on this array. And the arguments object is a popular example of an array-like object. It's not a real array. So when you call array built-ins, such as for each on it, it actually works, but it won't be fully optimized the way it would be for a proper array. Now, there is a solution for this as well. ES 2015 has this feature called REST parameters that can actually help you with this. They produce proper arrays that can be used instead of the array-like arguments object in a very elegant way. So nowadays, I think there's no good reason to use the arguments object directly anymore. You should use REST parameters instead. It makes your code more elegant, and engines can also optimize it more efficiently. This is not a real crocodile, and it's not going to have the same performance as a real crocodile. The same thing goes for arrays. In general, you should avoid array-like objects whenever possible and use proper arrays instead. Okay, so after all this talk about elements kinds, you may be wondering how to identify the elements kind of some array in your code base. This might come in handy when you're debugging a performance issue or just when you want to get a deeper understanding of what I've been talking about. Well, luckily, whenever V8 is built from source, it produces this binary that you can run from the command line. It's called D8, and it stands for, I think the D stands for debug or developer. No one on the team really knows for sure. It's kind of a mystery. But anyway, if you run D8, it offers a read eval print loop, a REPL, just like when you run Node.js on the command line. And it makes it easy to run some code directly in V8 without having to go through an embedder like Google Chrome or Node. You run it directly in V8 itself. So to find out the elements kind of an array, you can open your favorite shell and then run a debug build of V8. You pass in this allow native syntax flag, which enables some internal V8 functionality from within JavaScript. And entering that command opens up the REPL I talked about. So now we can start entering some JavaScript code. So first we create the array that we want to test. And then we call one of those special V8 functions on it. In this case, we use debug print. You see how the name there starts with a percentage sign? Well, that's not really valid JavaScript. That's why we actually do this for a reason. We don't want people to use this in production code because it wouldn't work in the first place. It's only useful for debugging, and it only works in this particular configuration of V8. It needs to be a debug build of V8, so it won't work in a browser, for example. So anyway, running this code prints a lot of output, even more output than what you can see here on the slide. But in this case, what we're looking for is the elements kind, which is listed on this line. In this case, the elements kind is holy smy elements cow. And the cow does not refer to the animal. It stands for copy on write, which is yet another internal optimization. But don't worry about that for now. That's a topic for another presentation. So let's recap. We've explored what elements kinds are and how they work. And as a result, we were able to identify some practical performance tips that can help us boost performance. So the first one is avoid creating holes in arrays. Don't access indexes beyond the array's length. Try to keep the elements kind of your arrays as specific as possible by sticking to a single value type for each array. Avoid using array-like objects, and when you have to use them, consider converting them to proper arrays before performing any expensive operations on them. Now, although this presentation covered V8 internals specifically, these tips don't just apply to V8. Other JavaScript engines can benefit from them as well. So by following this advice, I promise you your code is going to be cleaner, simpler, and it's not going to get any slower in other engines. In fact, it might actually get faster across the board. There is one more thing that I want to mention for you. We briefly talked about this pattern where you have an array, and if you know all the values ahead of time, you can just put them right inside of the array literal, right? But what about the case where you have lots of values? You have a very large array, and you don't know all the values ahead of time. Maybe you're computing them dynamically. In that case, you may have seen this pattern being used before. If you know the length of the array ahead of time, but you don't necessarily know the values, you can pass the length to the array constructor like this. And there's actually a benefit to this that I didn't mention earlier. Doing so ensures that JavaScript engines can pre-allocate the space for the 9001 elements that are needed for the array. The downside, of course, is, as we discussed before, the array will be marked as holy because it contains 9001 holes as soon as it's created. So it's really a trade-off. When you're using the array constructor like this, JavaScript engines can pre-allocate the space for the correct number of needed elements behind the scenes. And especially for large arrays, this might actually speed up the creation of the array. However, the array will be marked as holy from the beginning, resulting in potentially slower array operations compared to packed arrays. Then we looked at this other pattern where instead you start with an empty array and then you just push all those values to the array to avoid going holy. Now, what happens in this case is when you create an array, the JavaScript engine needs to initialize a buffer in its backing store to hold all the elements in the array. And as soon as you create an empty array in V8, we initialize a buffer with room for 16 elements to give it some room to grow. But whenever a new element is added that doesn't fit in the buffer anymore, we have to reallocate, which means behind the scenes we have to create an entirely new array in the backing store, and then we have to copy all those 16 elements over, which is kind of an expensive operation. So if you start off with an empty array and then you push 9001 items to it one by one, V8 will actually have to reallocate the buffer in the backing store a total of 16 times. So you can imagine that for larger arrays with millions of items, that's a lot more reallocations, of course. So starting from an empty array and then continuously pushing to it ensures we never create any holes. The array remains packed, which is good for performance for future operations on the array. But when you look at the downside, it's actually the creation of the array might become a little bit slower because behind the scenes, the engine will need to reallocate all the time. So this is really a trade-off. Either you choose to optimize the array creation itself by using the pattern new array passing in the length. so that the space can be pre-allocated behind the scenes, or you choose to optimize the later operations on the array. And in this case, it actually makes sense to avoid wholly elements kinds. So this is definitely a trade-off, and which of these options you want to go for depends on your exact use case and what you're trying to do in your code. But it's something to think about. And finally, the best advice that anyone can give you today is just write modern, idiomatic JavaScript and let the JavaScript engine worry about making it fast, because that's the JavaScript engine's job. Thank you so much for listening.